Hi, I'm Jonathan, and I'm going to talk to you about our team's design approach. To maximize the performance of the turbine, we came up with different designs, from the classic windmill-style turbine that uses lift to generate power to the horizontal turbine that uses the forces of drag. I would say that our group was coming at the project from the approach that the turbine efficiency and performance were the highest priority. We came into the project with high expectations on what we could accomplish based on what we heard in lecture, with the idea that since we were in E2 engineering building for discussion periods, we would have access to a plethora of tools and other equipment in the workshop. As we soon realized, there was a lot less equipment than we thought, but we still wanted to get creative to meet the stretch goals for performance and efficiency. While we did want to do this, we were also thinking about the price that came with putting a lot of fancy parts and additions into our turbine. Something that benefited us in the way of price was the fact that the lighter the spinning part of the turbine was, the easier it was able to spin, meaning that as long as the materials were strong enough, the lighter the material, the better. This made efficiency an easier task. While we were trying to make the turbine light, we realized that one of the stretch goals for weight was not having to clamp down the turbine. We realized that if we made the parts of the turbine that were in motion lighter, it would take less energy from the wind pushing on it to start and sustain the spinning motion. While if we made the static parts heavier, we wouldn't have to clamp down our turbine, making a turbine that was overall very effective but completed other goals as well.
Hi, I'm Matt. I'm going to talk to you about our performance data that we got from measuring the wind turbine, and then I'm going to show you a model of the entire thing. We wanted a program that would record and plot our generator's performance. The whole program is about 30 lines of code written in MATLAB. It asks you when you want to start measuring, and then it waits until it detects a voltage produced by the generator. Once it does, it records and then plots 100 data points for voltage and current. We generated an average of about 0.08 volts at 0.4 milliamps, and we confirmed this on testing day using a multimeter. Here's a quick video of the first working test with the program running. We'll start with an isometric view of our turbine. In this model, we've removed the outer housing and the tower so that you can get a better idea of what's going on. I think the first thing most of you will notice is these 4 Archimedean turbine blades. So next let's talk about how we're getting the power from our blades to the generator. First is this large rubberized wooden disc that's mounted to the drive shaft. While we're over here, I should mention how that shaft is supported by these roller bearings in the housing. Between the large disc on the drive shaft and the smaller one mounted to the generator, we were able to achieve about a 4.5 to 1 drive ratio.
Hello, my name is Lang, and I'm going to talk about the parts of our project, and we will discuss the price and how we use them. For this project, we bought a lot of stuff. We have 18 inches of quarter dowel, 53 of 1/8 dowel, and 5 inch of 1 dowel. Those wooden dowels cost 7.25 SSP. We have 9-ton depressors. Those cost 27 SSP. Also, we already spent $10 on bearings. We cut 2 sheets construction paper for the blades of the rotor. That is 4 SSP. Also, we used hand saw, hot glue gun, and drill for many times in the class. We purchased a 4 inches wooden disc for 15 SSP. The 3 tools cost us 60 SSP. Finally, we spent 143.25 SSP for the completed projects.
Hi, I'm Brian Chevron, and here I'm going to talk to you about all of our failures, but more importantly, our successes. The final design did not come immediately to mind, and many iterations were executed before our final was actually built. Our base was designed to be universal for any variations of our fan design, and our fan design went through a total of 4 iterations. Most of our failures went into either designing something that was either too inefficient to be put into use or was too complex to build. For example, the impeller fan was too complex to build, and the drill fan was too inefficient. Our final design came in a massive success. Our turbine was stable, it was very cost efficient, and it produced peak power. Our final iteration of the fan, the Archimedes sail fan, was very, very simple to build, it was very efficient, it was very light. Our base overall did not go through very, very many iterations. The structure had to be raised a tiny bit in order to let the fan clear, but other than that slight hitch in design, our base stayed relatively the same throughout all production. We changed the support structures to 3D printed pieces. They seem to prove very, very malleable and also very, very stiff through our build process. Our final iteration of turbine to motor linkage came in the form of rubberized wheels. These proved to be the most stable, the most efficient, and the most dependable. This is our final design here. This is the Apollo 26, signing off.